Hello chemistry champions, this is Werner. Welcome back to the channel. In today's video I'm going to show you how to calculate the formation enthalpy of glycine from the somewhat limited information provided. These types of questions are common in the physical chemistry branch of chemistry, specifically thermochemistry. By the end of the video you will be familiar with balancing a combustion reaction and be reminded of the definition of formation enthalpy, or more specifically the standard enthalpy of formation. Let's have a look.
Right, so let's get started with today's problem, which asks the question, can we calculate the enthalpy of formation for glycine? Now, the first thing is we were given just the formula for the glycine, and we're going to have to know what is the actual formula. We're given the structure, and we need to figure out what is the formula. So that should be quite easy. You have 2 carbons. You have 1, 2, 3, 4, 5 hydrogens. You have 2 oxygens and a nitrogen. So the formula for the glycine is C2H5O2N. So you were given the enthalpy for the reaction, and so you're going to have to know what is the balanced equation. And so the way one can do that is to start with the glycine, C2H5O2N, and that is a solid. It's important to designate the phase, as I'll explain later. Plus you have oxygen gas, that refers to the combustion, and then you have carbon dioxide gas, that is a byproduct of any combustion reaction for organic compounds, plus water, H2O, liquid, plus nitrogen gas. I'm going to assume that it's complete combustion. That means you form N2. If it's incomplete combustion, you'll form some NOx gases, so-called NOx gases. But because you were given no information on that, one will have to assume that it's complete combustion that's taken place. So the next thing is one will have to balance the equation. Now there's different ways in which one can balance the equation. The way that I have found to work quite well is to look at all the different elements on the reactant side and all the elements on the product side. So you have carbon, hydrogen, oxygen, and nitrogen. And similarly on the product side, here you have 2 carbons, here you have 1 carbon, here you have 5 hydrogens, here you have only 2, here you have 2 plus 2, that's 4 oxygens on the product side, and you have 1 nitrogen, and here you have 3 oxygens, and you have 2 nitrogens. So what one can then do is you typically look at what is the highest number, and you can start there. So for hydrogen, you have 5 and 2. So the only way those two can be made equal is if you multiply this with 2 there, and you multiply this with 5. That gives 10. Sorry, 5. 5 times 2 is 10. Right. So then one look at the carbons. So here you have 4 carbons. Here you have only 1. So this one requires 4. So this is times 2. That's 4. Times 4 gives 4. So now the carbons have been dealt with. The oxygen is a bit complicated because you have oxygen split across different reagents. And so you don't know yet what is the respective ratios. But with the information one has, you could say that you have 4 4 oxygens, and here you have another 2, and here you have 8 plus 5. So on this side you have 13 oxygens altogether, and if you deduct the 4 here, that leaves 9, and that then is what's needed to balance the oxygen. But you have 2 atoms per oxygen molecule, so then this becomes, divide by 2 is 4.5. But because one typically don't leave it as a fraction as 4.5, what one can do is you can multiply right through by 2. So that means the final coefficients here would be 4, 9, 8, 10, 2. And so that reaction now is balanced. And so then one can move on to the next step. Now, one of the things that one is given is the enthalpy for the whole reaction. That's one thing that was given. And then one were given the formation enthalpy for a number of compounds in the reaction. And so it's a good idea to just summarize what is the standard enthalpy of formation. It's defined as the enthalpy change when 1 mole of a pure substance is formed from its elements. The elements must be in physical and chemical form, which is the most stable. And this is important because the element in its stable form has a formation enthalpy of 0. And if it's not in its stable form, then it has some value in kilojoules as to what its formation enthalpy should be. So for example, we know that bromine, for example, is stable as a liquid. And so the formation enthalpy for bromine in the liquid state would be 0. But in the solid state, it would have some value. That's why it's important here to show what are the respective phases that one is referring to. For example, here for the nitrogen, this will be 0 formation enthalpy because nitrogen as a gas is natural in its chemical and physical form. If this was a liquid, i.e. liquid nitrogen, then that value will not be 0. So that's how we can work out those problems. And then the last thing I want to say on that, just on terms of notation, is that you typically write it like this. This is just to say this delta means change in enthalpy, and the 0 there means standard conditions, and the F here means formation enthalpy. That just designate what enthalpy. The H, of course, is enthalpy. And what enthalpy are we referring to? Because there's a whole host of different enthalpies that one can calculate. Sublimation enthalpy, evaporation enthalpy, etc. So there's a whole list of those. So this just makes sure that we are dealing with the right thing. And then one needs to talk about what, when we refer here to the 0 standard conditions, what are the standard conditions? Are we referring to STP conditions? So we know, for example, with STP, STP conditions, that is 0 degrees Celsius. That means standard temperature and pressure. It is 32 Fahrenheit. It is 273.15 Kelvin. These are the temperatures. And pressures, you have 1 atmosphere, which is 101.325 kilopascal. You can also say 760 torr mercury. So these are the pressures. So STP standard temperature and pressure, that does not apply when one talks about standard conditions in enthalpy calculations. So it was decided that the standard conditions is defined slightly differently. The temperature is not 0 degrees, is 25 degrees Celsius. That translates to 298.15 Kelvin. And the pressure is also different. This is the temperature. And the pressure is 1 bar, which is 100 kilopascal pressure. So these are the standard conditions when we talk about that 0. That refers to these conditions. So just keep that in mind as well. Right, so with all of that out of the way, we can start to make a calculation. The first thing one wants to typically do is to write down the general reaction. That is basically the sum, designated by this epsilon, of the coefficients of the standard formation enthalpy of the products minus the sum of the coefficients of the reactants. And we were given this value in the problem. That's minus 3857 kilojoule. And that is equal to, let's put this in block brackets, 8. So now we're dealing with the coefficients of the products. So we see there 8. And this is for the carbon dioxide, plus 10 for the water. I'm not putting the phases again. You know now we're dealing with these phases. Plus 2 times that for the nitrogen, minus for the glycine, plus 9 formation enthalpy for the oxygen. Close the block brackets. Right, so now what we can do is we can fill in the formation enthalpies for these different species in their respective phases. So we have times 8. This value was given, negative 393.5, plus 10 times the formation enthalpy for the water in the liquid phase was given, negative 285.8, plus 2, 0, right? The 0, because of the nitrogen in the gas phase, is 0. Minus. Now we're moving over to the products, sorry, the reagents. For, in the balanced equation for the glycine, C2H5O2N, plus 9 for the oxygen, which is 0, gives that value. So now we have negative 3857 kilojoule is equal to negative 3148 minus 2858 minus 4 for the glycine, and then 2149 kilojoule is equal to minus 4 delta HOF for the glycine. So 2149 kilojoule divided by 4 negative, that is equal to negative 537.25 kilojoules per mole. And if one wants to be fussy about significant figures, that will be the last significant figure, just because in this part of the answer you were given this value and there were no decimals involved there, so there cannot be decimals involved in the final answer. So the final answer I have is negative 537 kilojoules per mole. And there we've solved for the enthalpy of formation for glycine. You can see it's an exothermic reaction.
That was a good example to calculate the standard enthalpy of formation for glycine from the specified information. I hope you found it of value. Let me know in the comments if you'd like to see more examples of thermochemistry related problems. Please consider to subscribe to the channel for similar content. Stay curious, check out my other videos on the channel where we solve interesting chemistry problems. Thanks for watching, have a great day, and I hope to see you in the next video.